Good day, students. In this clip, we're going to be going over an example on optimization and modeling. This situation involves a cylinder being inscribed in a cone and determining the maximum volume. Okay, this is part 2 of a 3-part series, so you can go to my playlist to access the other parts. Okay, so when solving optimization problems, these are the 5 steps I normally require of my students. First of all, you generate a model using a well-labeled diagram. The models are going to be two. You're going to have your optimization, a primary function, and a constraint function. Okay. Part 2 involves a substitution process where you're going to express your optimization function in terms of one variable by substituting and explicitly solve for variable in your constraint function into the optimization function. That makes it easy for you to differentiate. Okay. And then you also state the domain, the reasonable domains for your new function in terms of just one variable. In part 3, you're going to find the potential extremas. Those include the endpoints and the critical points. Endpoints are applicable to use both interval situations. And in part 4, you're going to classify your extrema using the using the second derivative test is basically the fastest way to do that. And then lastly, um, you state the meaning of your result. Okay. All right. So let's take a look at the example. This is number 3. It says a right circular cylinder is inscribed in a cone with height 12 and base radius of 4. Find the dimensions of the cylinder that maximizes its volume, the volume of the cylinder, and what is the maximum volume of such a cylinder. Okay, so this is a graphic I have right here of a cylinder inscribed in a cone. Let's start by creating a model. I need 2 equations. I need my optimization function, and then I also need my constraint function. All right, so let's start out with the optimization function. Optimization, the function to be optimized, optimization function. All right, so we're optimizing the volume of a cylinder. So what is the volume of a cylinder? We know it's the area of the base times the height. So what I'm going to do is I'm going to create a 2-dimensional replication of this situation right here. So let's say we have in 2 dimensions, this is the cylinder right here. Okay, so let's do it this way. All right, so that's the cross-section representation of this situation right here, sliced down the middle. So this is the cone, and this is the cylinder right here. So let's do it this way. Let's say that we want to call the height of the cylinder. This is the height. Let's say the height is y, and we're going to call the radius of the cylinder x. Okay? We do not know what they are yet, right? So we're going to use variables to represent them. Okay, so the height of the cylinder is y, and the base radius, let's call that x. Okay, all right, so now that we know the height and we've declared the height, the variables for the height and the radius of the cylinder, now we can find the volume, okay, which is what we are optimizing. So we know that. Let me just write down the formula for volume before I use it. So volume is equal to pi r square h, area of the base times the height. So in this case, v is going to be pi, the radius is x, so it's pi x square y. Okay, so that's the optimization function for you. Now, the constraints. What are the constraints on the dimensions of the cylinder? So constraint or the secondary function. So for the constraint, we're constrained by the dimensions of the cone. Okay, so we have this triangle right here. This rectangle, the cross-sectional dimensions of the cone must reside inside, the rectangle must reside inside that of the cone. All right, there are 2 ways that we can find the equation for the constraints. One method is by using similar triangles, and the second method is by using the equation of a line. All right, I'm going to show you both methods, and then you can basically pick the one that you like the best. Okay, I prefer similar triangles because it's straightforward, and I don't need to, do any hard work with that. So let's see. If I want to use two similar triangles, I need to basically make a statement that corresponding sides of our similar triangles are in proportion. So we have the entire length of the cone. We know the cone has a height of 12 units, and the radius of the cone is 4 units long. Okay, so there goes the radius of the cone. So now I'm going to use the similarity postulate here to state that the angles are similar. Well, how do we know that our two triangles are similar? Well, first of all, what two triangles am I talking about? Let me highlight them for you real quick so you can see. This is a smaller triangle right here, the red triangle. Okay, this is a smaller triangle right here. And then the bigger triangle, the entire thing is the bigger triangle. Okay, let me put that in, let's put that in green so you can see the two similar triangles that I speak of. They're green. Okay, so see this triangle right here? This big one. This one is the other triangle. Okay, that one right there. So the green triangle is similar to the red triangle. Okay, so how do we know that they're similar? Well, since this side, this vertical line right here is parallel to this vertical line right here, um, these two angles form corresponding angles. So these two angles are congruent, okay? And then these two angles are the same. They share a common angle here. So by the angle-angle similarity postulate, we can conclude that these two triangles are in fact similar. So this side corresponds to the entire length, and this side corresponds to this side right here. Okay. All right. So we need to find the dimensions of our smaller triangle. Okay. So we know that the height is y of our smaller triangle, but we need to find out the base. This distance right here. So since the entire thing is let's change the color of that. Since the entire thing is 4 units long, and we know that this portion is x units, so what's going to be left here is the question. So if the entire thing is 4 units and this portion is x, what's going to be left is the difference, right? It's going to be 4 minus x. Okay, so we have this big triangle right here that is 12 by 4, and we have a small triangle right here that is y long by 4 minus x. Okay, all right, so let's state it right here. Method 1, for finding the constraints, method 1 is using similar triangles, all right, similar triangles. All right, so just to make sure everybody understands this, I'm not trying to bore you here. I'm just going to draw the two triangles separately so you can see what I am doing. So we're going to draw first the bigger triangle, and then we'll draw the smaller triangle that it's similar to. Okay? All right, so I'm now going to populate the measures, and then we can use the similarity postulate to basically make statements about the proportionality of corresponding sides. This entire side is 4 units long. This side is 4 minus x. This length right here is 12 for the big one, and then for the small one, this is y. All right, so corresponding sides are basically in proportion. So what statement can we make here? We can say that y, the height of the smaller one, the y over 12 is equal to 4 minus x, the shorter leg of the small one, divided by the shorter leg of the big one over 4. Okay? So this is basically elementary geometry we're using over here. All right, so that statement, I like to isolate a variable so I can make a substitution here. So we have two variables. So what I can do here is I can get y isolated by multiplying both sides by 12. Okay, so I multiply this by 12, and then I multiply this side by 12 also. So what's that going to yield? It's going to give me y equals 4 goes here 1, 4 goes here 3 times. Distribute the 3, 12 minus 3x. Okay, that's a nice constraint. So that's one way of doing it, using similarity. Another way of doing it is by using the equation of a line. So method two, we're going to use y equals mx plus b. Okay, now to do that, just imagine that this right here, this is your y-axis, okay? And then imagine that this right here is your x-axis. All right, so, and then this side right here is the equation of a line, and this is a point on the line, okay? So, what is the equation of this line right here? If you look at this line, this is a y-intercept. If you're going from 0, 0, all the way, let me make my y-axis a little bit longer so it's obvious what I'm doing. Let's put the line here 1 second. So that's 0, 0, coordinate system. Give me what directions. Okay, so if that is 0, 0, and you go 12 units up, so what's the y-intercept of this line going to be? This entire line right here, if you go 12 units up, it tells you that y-intercept is b, which is 12. So for that case, we know that b is going to be 12. That's your y-intercept. Okay, now what is the slope of this line? Starting from 12, you drop down 12, that's your negative rise, and you run 4. Okay, so m is rise over run, which is negative 12 because you're dropping, and your run is 4. And if you reduce that, you have negative 3. All right, so if you plug in b and negative 3 into the y equals mx plus b equation, you have y equals negative 3x plus 12, which is the same thing as what we had before. What did we have before? 12 minus 3x is the same thing as negative 3x plus 12, because we know about that addition commutes, okay? So that's basically our constraint function. All right, so whichever method you like, you can use. I like this one better, so that's the one I use. So let me box my constraint function. This is my constraint function right here. Variation 1 or variation 2, they're the same. And then my optimization function is this one right here. All right, let's move on to part 2, where we're going to be doing this substitution. All right, so part 2, we're going to substitute. The nice thing here is that we have already isolated a variable in our constraint function, so we don't have to do much work. We know that v in terms of two variables was pi xy square, x square y. And then when we make a substitution, we know that this is this, and y is equal to 12 minus 3x. So if we make the substitution of this value of y in here, our volume function that we're going to be optimizing in terms of just x is going to be pi x squared times 12 minus 3x. Okay? And then to make it easy to differentiate so we don't have to use the product rule, we can just distribute pi x squared to these two terms right here. So v of x is going to be 12 pi x squared minus 3 pi x to the third. Now what's the domain? What is the domain here? What are the constraints on x? How small can x get? Well, let's look at the triangle. If this cylinder were to have 0 radius, it would just be a long straight line, right? So if that is zero radius, you have just a straight line. It's going to be a line. That's as small as x can get. How big can x get? X can get as wide as this. Okay? In that case, you have a flat line as your cylinder. Okay? So when x is 0, you're going to have a situation like this. You have a cylinder that looks like this. I don't know why you want to have a cylinder like that, but that's the situation when x is 0. And then when x is the maximum value of 4, you're just going to have a line that's 8 units long and has 0, and it has a 0 height. Okay, and that will also yield a volume of 0 also. So these are your two extremes. X can be 0, or x can be equal to 4. Okay, remember x is your radius, it's not your diameter. Okay, so that's x right here. Okay, so our domain is um, x goes from 0 to 4, there are no restrictions on this because it's a cubic function, no domain constraints, so these endpoints are good. All right, so let's move on to part 3. We're going to look for potential extremas. Extremas. All right, so the endpoints are automatically potential extremas that will be considered and should be considered, but we also have to find the critical points, okay? Because we know potential extremas are your endpoints and critical points, okay? All right, so we already know our endpoints, so let's look for our critical points. So critical points, what are critical points? Critical points are where are critical points? Where the v prime in this case, because this is a function, v prime is equal to 0, or v prime does not exist. That's what our critical points are, all right? So let's focus on the first one, where is v prime equal to 0? So let's recall the volume function. V of x is equal to 12 pi x squared minus 3 pi x to the third. Let's find the first derivative of that. V prime of x is equal to 24 pi x minus 9 pi x squared. All right, so set that equal to 0. You have 24 pi x minus 9 pi x squared equals 0. So let's factor out, I'm going to be lazy here, I'll just factor out x, even though that's not the GCF. So factor out x, and then you're going to be left with 24 pi minus 9x equals 0. Now we're going to use the zero product property, set x equal to 0, or the other one, 24 pi minus 9x equals 0. This is already solved. This one is going to be x equals 24 over 9, right? Oh snap, here's a pi here. Sorry about that, let me put that back in. Kind of drop the pi off in the process. So put the pi back here, pi x. Okay, equals 0. So when you solve for pi, you have negative 24 pi over negative 9 pi. Okay, which reduces to divide both sides by 3, 8 over 3. Okay, so that's your x value. You notice that one of our solutions intersects with the lower bound of our domain, right? Okay, so now, when is v prime non-existent? This is a cubic function. We don't have any corner, cusps, vertical tangents, or discontinuities. It's smooth and continuous, so it's always differentiable. So when is v prime dne? Never. Okay. All right. So our potential extremas that we're going to consider, potential extremas are the endpoints. Let's put them in increase. So 0, and then let's put it in order. 8/3 and 4. Okay? This is an endpoint and a critical point. This is a critical point, and this is an endpoint. So these are the three things we're going to evaluate to find the maximum. Okay? All right, now let's take a look at part 4. That involves classification of the extremas. It turns out that for this problem, we don't even have to use the tool of calculus to determine which is a max or a min. We can just evaluate these points, put these points into the function, and then we can tell if they're maxes or minimums. Okay, so let's see. Let's call it classification or classify. All right, so since these are our endpoints and critical points, if we plug all of them into the function, the biggest one would tell us that's basically the maximum. And then if we have smaller ones, they could be relative mean or absolute mean, whatever, but let's just plug them in and see what we have here, okay? So we talked about the endpoints earlier as creating zero volume. So if we do v of 0, for example, plugging 0 into the original function, 12 pi times 0 squared minus 3 pi times 0 to the third. That's going to be 0. And then even though if you compute via 4, 12 pi times 4 to the second power minus 3 pi times 4 to the third, plug that into your calculator, you'll get 0 also. Okay? Now let's plug in this one, v of 8 over 3. V of 8 over 3, we're going to have 12 pi times 8 over 3 squared minus 3 pi times 8 over 3 to the third. If you plug this in your calculator and work this out, you're going to end up with 256 pi over 9. Okay? So you can clearly see that this is the maximum. It's an absolute, it's a relative and absolute max. Relative and absolute max. And then these right here are your minimum. But we don't really care about these. We just care about the biggest volume, so to speak. Okay, so this is the biggest volume. And then we're going to conclude that these are the minimums too, because there's no way you can have a negative volume. Okay? All right, so this is our absolute max right here, just by plugging in. But you can also verify using calculus. Okay, so let's just do x right here. This is not necessary, but if you wanted to verify using the second derivative test, all you need to do is you have a critical point, and if the second derivative is negative, you have a downward concavity or it's concave down, and that indicates that you have a maximum at that critical point. All right, so we know that v prime of x was equal to 24 pi x minus 9 pi x squared, and then the second derivative v double prime is going to be 24 pi minus 18 pi x. Okay, so we want to evaluate the sign of the second derivative at this critical point. I just want to show you that this is in fact a maximum. Okay, so we're hoping to get a negative output, so that will indicate downward concavity, and then that will tell us that it's a maximum. Okay, so v double prime of 8 over 3 is equal to 24 pi minus 18 times 8 over 3, 18 pi times 8 over 3. Okay, that equals 24 pi minus 3 goes here 1, 3 goes here 6, 6 times 8 is 48. So 48 pi. And then when you subtract it, you have negative 24. So negative 24 pi. So v double prime is negative here. Okay, so since 8 over 3 is a critical point, and v double prime of 8 over 3 is negative, there is an absolute maximum at 8 over 3. Okay, because you know what downward facing concavity looks like, right? It looks like this. So if you have a downward facing concavity at an extrema, that is absolutely a maximum. Okay, all right, so that's that for the classification. We found a maximum, but that's just the x value. We have to state the dimensions of the maximum area. Okay, maximum volume. So part 5 is our conclusion. Let's state the dimensions first. Dimension of maximum volume of a cylinder with maximum volume. Cylinder with maximum volume. The radius is x, right? So the radius is x, and x is 8 over 3. And then the height, remember what we said the height was earlier? The height is y, and that's given by 12 minus 3x. And then we know x is 8 over 3, right? So it's 12 minus 3 times 8 over 3. 3 goes here 1, 3 goes here 1, 8 minus 12 is 4. So the height is 4, the radius is 8. Okay? And then the maximum volume is what you get when you plug in 8 over 3 into the original function. And I think we've already done that. We did that right here when we're determining which one is the maximum. So V of 8 over 3 is the maximum volume, okay? So we're going to do simply V of 8 over 3, and then we have 256 over 9 pi. All right, and this is in cubic units. This radius is in units, and your height right here is in units. Okay, so there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. I really appreciate it. And please post a comment to let me know what you think about this clip, and give me a thumbs up if you liked it. More clips can be found on my website.com/calculus. Thanks again for watching, and have a wonderful day.